For decades, the human imagination has been captivated by the vision of a permanent red city on Mars. We see gleaming pressurized domes standing against salmon-colored skies, hydroponic greenhouses feeding generations of pioneers, and heavy rockets landing on dusty launch pads to deliver the vanguard of a multi-planetary species. It is a grand, inspiring vision of technological triumph, the ultimate insurance policy against terrestrial extinction. But between the heroic rhetoric of interplanetary settlement and the physical reality of deep space lies a terrifying wall of scientific, physiological, and logistical constraints. Building a temporary science outpost on Mars is well within our technical reach. Establishing a self-sustaining permanent civilization is a fundamentally different challenge. When we examine the harsh thermodynamic truths of the Martian environment, a sobering possibility emerges. The first human colony on Mars may not collapse in a sudden, dramatic catastrophe, but rather fade away in a slow, irreversible decline long before it ever achieves independence. If you enjoy calm, scientifically rigorous explorations of spaceflight, planetary science, and the quiet realities of the cosmos, please consider subscribing to the channel. Settle in, relax, and join us as we examine the hidden limits of human survival beyond Earth. The public narrative surrounding the colonization of Mars is often dominated by the sheer spectacle of interplanetary rocketry. We marvel at massive stainless steel hulls glistening under Florida sunlines, methane-fueled engine clusters generating millions of pounds of thrust, and dramatic computer renders depicting armadas of cargo freighters departing Earth in synchronized formation. This visual emphasis on transportation creates a subtle but profound cognitive bias. It leads us to treat interplanetary migration as primarily a launch problem. The implicit assumption is that if we can engineer reusable rockets capable of delivering hundreds of tons of payload to the Martian surface at affordable costs, the survival and eventual independence of a red colony will naturally follow. Yet, this focus on the launch pad masks a terrifying logistical reality. Getting to Mars is merely a mechanical preamble. Staying on Mars requires replicating the foundational industrial capacity of an entire technological civilization on a barren world 400 million kilometers away. To understand the colossal scale of this logistical imbalance, one must examine the brutal mechanics of the orbital transfer window. Unlike travel between terrestrial cities, or even flights to the Moon, transit to Mars is dictated by the orbital alignment of two planets revolving around the Sun at different distances and speeds. Optimal minimum energy transfer trajectories known as Hohmann transfer orbits open only once every 26 months. When Earth and Mars align in their celestial dance, each transfer window opens a narrow operational period during which payloads can be dispatched across the interplanetary gulf, requiring a journey of 6 to 9 months through deep space. This celestial rhythm means that a fledgling Mars colony is not connected to Earth by a continuous, real-time supply pipeline, but by an intermittent, highly vulnerable pulse that fires only once every 2 years. If an emergency arises between these alignment windows, a catastrophic crop disease in the hydroponic bays, a systemic failure in the water recycling pumps, or an unforeseen degradation of vital electronics, no emergency resupply ship can be launched to save the crew. Earth cannot send aid on demand. A colony on Mars must be capable of surviving for over 700 days on whatever reserves it has on hand, with absolute zero possibility of external intervention. This spatial and temporal isolation transforms every technical malfunction from a routine maintenance issue into an existential crisis. A single missing component, a ruptured valve, or a depleted chemical reagent cannot be ordered from a terrestrial warehouse. It must either be manufactured locally from raw planetary materials or waited out for years while crew members ration survival margins. Furthermore, the payload logistics required to establish even a tiny permanent outpost challenge the fundamental limits of aerospace production. Consider the basic physical mass required to support a human life over extended periods. A single human consumes roughly 800 grams of oxygen, 2.5 kilograms of water, and 600 grams of dry food every single day, while producing metabolic waste that must be processed. Multiply these basic biological requirements across a modest pioneer population of 100 individuals over a 2-year operational cycle, and the biological consumption alone exceeds hundreds of tons of material, even with highly efficient recycling systems operating at near-perfect capacity. When one adds the non-biological infrastructure pressurized habitat modules, radiation shielding, nuclear reactors, solar arrays, drilling rigs, chemical processing plants, rover vehicles, spacesuits, medical facilities, and millions of specialized replacement parts, the required mass explodes into tens of thousands of metric tons. Delivering this initial infrastructure to the Martian surface would require hundreds of heavy rocket launches from Earth, representing an economic and industrial effort greater than the construction of the International Space Station, multiplied by orders of magnitude. Yet, even if Earth possesses the economic willpower to land this initial mass on Mars, it merely establishes an artificial enclave entirely dependent on constant terrestrial resupply. The true delusion lies in the concept of self-sustainability. A self-sustaining colony is not merely one that grows its own potatoes and recycles its own water. It is one that can independently produce every piece of technology required to maintain its survival, without importing specialized components from Earth. Consider the microchip running our oxygen scrubber's sensor valve. Manufacturing a single modern integrated circuit requires a global industrial supply chain on Earth, encompassing hundreds of specialized chemical factories, ultra-pure silicon refineries, extreme ultraviolet lithography machines, precision optics, and rare earth mining operations spanning dozens of nations. If a critical microchip fails inside a Martian life support unit, the colony cannot simply fabricate a replacement chip from Martian sand using a 3D printer. It requires a multi-billion-dollar semiconductor fabrication plant that itself requires a massive industrial web to operate. This technological interdependence creates a severe threshold problem. On Earth, our industrial civilization relies on extreme division of labor and vast economies of scale. No single city, state, or even nation manufactures every component of its own infrastructure independently. We rely on an interconnected global network. For a Mars colony to achieve true self-sustainability, the point where it can survive if Earth suddenly ceases sending supply rockets forever, it must replicate this entire technological ladder locally. It must mine ores, refine metals, synthesize complex polymers, manufacture precision bearings, forge specialized alloys, build optics, refine pharmaceuticals, and produce microelectronics, all within a sealed, artificial environment powered by limited energy budgets. Until that immense industrial threshold is crossed, a Mars colony remains an umbilical parasite, a technological construct utterly dependent on the continued stability, wealth, and political willpower of the home planet. If an economic collapse, a global war, a catastrophic pandemic, or a shift in political priorities occurs on Earth, the intermittent supply ships will stop flying. The moment those 26-month supply pulses cease, the clock begins ticking for every human on Mars. The outpost will not collapse because its pioneers lack courage or intelligence. It will collapse because the complex technological machinery keeping them alive will gradually wear down, component by component, until the threshold of lethal failure is crossed. Consider the historical precedent of isolated terrestrial outposts. When European nations established colonies in distant oceans during the Age of Sail, those settlements frequently failed despite existing in environments with breathable air, liquid water, fertile soil, and abundant local flora and fauna. Colonies like Roanoke in North America or early settlements in Greenland collapsed when supply lines were interrupted for just a few years, on Mars, where the natural environment is actively lethal and provides zero atmospheric or biological support. The vulnerability to supply line disruption is infinitely absolute. We are attempting to build an industrial civilization on a world where a simple breach of a rubber gasket means instant death. Thus, the Launchpad narrative presents a dangerous misdirection. The fundamental hurdle to colonizing Mars is not designing a rocket that can reach the red planet. It is the staggering, almost impossible complexity of achieving complete industrial self-sufficiency before Earth's political or economic willingness to fund the umbilical cord runs out. If a Mars colony fails to achieve full technological independence before the supply ships stop coming, it will become an eerie monument in the red dust, a high-tech tomb holding the remains of pioneers who conquered interplanetary space, only to be consumed by the unforgiving arithmetic of terrestrial logistics. To further illustrate this industrial vulnerability, consider the maintenance cycles of complex environmental machinery. On the International Space Station, ECLSS hardware components such as pump assemblies, distillation units, and catalytic oxidizers frequently fail long before their predicted operational lifespans expire. NASA regularly flies replacement parts to orbit aboard cargo missions, relying on a massive inventory of spares maintained on Earth. On Mars, every machine must operate continuously in an environment filled with ambient dust and extreme thermal cycles. The rate of mechanical wear will far outpace the capacity of small on-site workshops to fabricate precision replacements, creating an ever-expanding maintenance debt that can only be settled by shipments from Earth. Furthermore, the energetic cost of interplanetary logistics imposes a permanent tax on terrestrial economies. Launching thousands of tons of cargo out of Earth's deep gravity requires consuming colossal volumes of refined propellants, occupying major launch facilities and diverting immense industrial resources away from terrestrial needs. During periods of economic hardship, environmental crisis, or geopolitical instability on Earth, funding multi-billion-dollar resupply missions to a distant scientific enclave will become politically unviable. A Mars colony that remains dependent on terrestrial resupply is perpetually living on borrowed time, vulnerable to every crisis that strikes the homeworld across the interplanetary void. Furthermore, the logistical infrastructure required to maintain interplanetary supply lines must account for orbital geometry mechanics. During solar conjunction periods, which occur once every 2 years when Mars passes directly behind the Sun, relative to Earth, radio communications between Earth and Mars are completely blocked by solar plasma for several weeks. During solar conjunction, ground controllers cannot transmit commands, and spacecraft cannot launch or land safely, creating a mandatory operational blackout where the colony is utterly cut off from terrestrial guidance and emergency support. This recurring communication and transportation blackout reinforces the absolute requirement for local operational autonomy. A colony cannot rely on real-time remote guidance from terrestrial engineering teams when an unexpected failure occurs during conjunction. Every system must be operated, diagnosed, and repaired by local crew members using locally available tools and documentation. If a colony lacks the internal expertise or specialized diagnostic hardware to resolve a complex failure during solar conjunction, the failure will compound across adjacent habitat systems, escalating into a systemic collapse before communications are restored. When early robotic probes transmitted the first color images of the Martian landscape, humanity beheld a world of striking, stark beauty. Sweeping crimson plains, majestic basaltic canyons, and towering extinct volcanoes stretched toward a pale pink sky. To the untrained eye, Mars resembles the arid deserts of the American Southwest, or the high, desolate plateaus of the Andes. It is easy to look at these landscapes and picture high-tech machinery clearing roads, agricultural domes anchoring themselves in red dirt, and human boots stepping confidently across dry riverbeds. but this visual similarity masks a sinister physical threat that coats every square centimetre of the planet Martian dust. Far from being harmless, familiar sand, the fine powdery material covering Mars is toxic, chemically reactive, and mechanically aggressive substance that presents a relentless hazard to both machinery and human biology. The primary chemical threat embedded within Martian dust is the presence of toxic salts known as perchlorates. Discovered in high concentrations by NASA's Phoenix lander, and later confirmed across the planet by the Curiosity and Perseverance rovers, perchlorates compounds containing chlorine and oxygen, such as magnesium and calcium perchlorate, make up between 0.5 and 1% of the Martian soil by weight. On Earth, perchlorates are rare, industrial toxins used primarily in rocket propellants, fireworks, and explosives. On Mars, they are a pervasive natural constituent of the surface regolith. Perchlorates are powerful endocrine disruptors in humans, specifically targeting the thyroid gland by inhibiting iodine uptake, leading to severe metabolic disruption, neurological impairment, and systemic organ failure. For a human colony attempting to survive on Mars, perchlorate contamination is an unavoidable operational nightmare. Every time an astronaut steps outside a habitat module for an extravehicular activity, EVA, their spacesuit becomes coated in ultra-fine perchlorate dust. When they return through the airlock, this toxic powder is inevitably tracked into the living quarters, settling on surfaces, floating in the recirculating air, and contaminating habitat water systems. Even with sophisticated double-door airlock designs and suit port interfaces, where spacesuits remain mounted to the exterior wall, microscopic dust particles penetrate mechanical seals. Over months and years of habitat operations, chronic low-dose exposure to perchlorate dust will contaminate the crew's living space, threatening long-term human health and complicating attempts to use local soil for agricultural crops inside habitat greenhouses. Beyond its biological toxicity, Martian dust possesses physical properties that make it a terrifying mechanical hazard. On Earth, liquid water, wind weathering, and organic processes continuously erode rock fragments into rounded, smooth sand grains. Mars, however, has lacked liquid surface water and a thick atmosphere for billions of years. Mechanical weathering on Mars occurs primarily through impacts, temperature fluctuations, and low-density wind transport, producing dust particles that are extraordinarily tiny, sharp, jagged, and abrasive. Martian dust particles average only a few micrometers in size, fine enough to behave like a microscopic aerosol that floats effortlessly in the thin atmosphere and penetrates even the tightest mechanical tolerances. This microscopic abrasiveness acts like a relentless polishing compound against every moving part on the Martian surface. When dust settles onto mechanical joints, bearing assemblies, airlock latches, and rover drive mechanisms, it rapidly degrades lubricants and grinds away metal surfaces. Solar panels, often proposed as a primary power source for early outposts, are particularly vulnerable. Fine dust layers settle onto solar cells, reducing power output by several % per month, while global dust storms can blanket the entire planet for months at a time, cutting off solar irradiance almost completely and starving a colony of electrical power. Cleaning solar panels with mechanical wipers or pressurized gas merely accelerates the scratching of protective optical coatings, permanently degrading their efficiency. The physical threat of Martian dust is further compounded by electrostatics. Mars is an extremely dry world with an atmospheric pressure less than 1% of Earth's, composed primarily of carbon dioxide. In this dry, low-density environment, dust particles moving across the surface, whether driven by natural winds or disturbed by human boots and rover wheels, accumulate massive electrostatic charges through triboelectric friction. Charged dust particles stick tenaciously to spacesuit fabrics, optical viewports, camera lenses, radiator surfaces, and habitat walls, defying simple mechanical brushing or blowing. This electrostatic adhesion creates a continuous maintenance crisis. When charged dust adheres to thermal radiator panels, which are essential for rejecting waste heat generated by habitat life support systems and nuclear reactors, it forms an insulating blanket that degrades thermal emission. If radiator efficiency drops significantly, interior habitat temperatures rise, threatening electrical systems and requiring energy-intensive cooling measures. On EVA suits, electrostatic dust coats flexible fabric joints, causing the material to stiffen, crack, and lose structural integrity far faster than suit designers anticipated during Earth-based testing. Consider the implications for agricultural plans reliant on local resources. Proponents of Mars settlement often suggest washing local regolith to remove perchlorate and using the processed soil to grow crops inside pressurized biodomes. However, washing perchlorates out of thousands of tons of toxic dust requires immense volumes of liquid water, which must itself be extracted from subsurface ice through energy-intensive mining. Furthermore, even if perchlorates are successfully leached out, the remaining crushed basaltic soil lacks organic matter, beneficial soil microbes, and essential nitrogen compounds, while retaining toxic heavy metals such as chromium, nickel, and lead. Converting raw Martian dust into fertile soil is not a simple gardening project. It is a complex, energy-consuming chemical engineering operation. The physical threat of dust also extends to breathing air quality inside human habitats. If fine Martian dust enters the interior atmosphere through airlock cycles or suit maintenance, crew members will inhale submicron particles deep into their lungs, like silica dust in earth coal mines or asbestos fibers in industrial environments. Microscopic basaltic dust particles cause severe pulmonary inflammation, fibrosis, and chronic lung disease. The sharp, unweathered edges of Martian dust cut into delicate lung tissue, leading to a condition similar to silicosis, silently degrading the respiratory health of colonists who are already operating under physiological stress. Thus, Martian dust represents a fundamental mismatch between human expectations and environmental reality. We view dust as a minor nuisance, something to be swept away with a broom or filtered out with a standard air cleaner. On Mars, dust is a reactive, abrasive, electrostatic chemical weapon that relentlessly attacks human lungs, compromises spacesuit integrity, grinds down mechanical gears, blankets solar collectors, and contaminates agricultural systems. It is an ambient environmental hazard that never sleeps, never stops, and never recedes. A colony on Mars will find itself locked in an endless, resource-draining war against an invisible, microscopic enemy. Thousands of operational hours will be spent cleaning airlocks, replacing worn seals, washing contaminated suits, scrubbing radiator surfaces, and filtering interior air. Over time, as mechanical components degrade and spare parts run low, the dust will gradually win the war of attrition. The failure of a Mars outpost may not come from a sudden hull breach, but from the slow, cumulative grinding of sharp red powder into the vital gears of human survival. To further understand the mechanical impact of dust abrasion, consider the seals on inflatable habitat modules and pressurized rover hatches. Elastomeric seals must maintain absolute airtight integrity against a continuous pressure gradient of 1 atmosphere pushing outward into the Martian vacuum. As fine dust settles onto seal faces during crew transitions, microscopic grit becomes embedded in the soft rubber compounds. Each opening and closing of a hatch grinds these embedded particles against mating metal flanges, creating microchannels through which habitat atmosphere steadily leaks into space, accelerating gas consumption and forcing life support systems to work harder to maintain pressure. Furthermore, global dust storms on Mars represent unpredictable operational catastrophes, occurring every few Earth years. These planet-encircling events lift billions of tons of fine dust into the upper atmosphere, blocking up to 99% of direct sunlight from reaching the surface for months at a time. During a global storm, temperatures drop, solar power generation collapses, and surface travel becomes virtually impossible. A colony reliant on solar energy would experience immediate power starvation, forcing life support systems to shed electrical loads and triggering life-threatening thermal survival modes in the freezing Martian winter. Additionally, dust storm dynamics on Mars introduce severe atmospheric heating and electrostatic discharge risks. During major dust storms, friction between airborne dust particles generates localized electrostatic fields capable of producing atmospheric glow discharges and surface electrical arcing. These electrostatic discharges present severe hazards to sensitive microelectronics, communications antennas, and external sensor arrays mounted on habitat exteriors and rover vehicles. Furthermore, airborne dust absorbs solar radiation in the middle atmosphere, causing regional atmospheric heating that alters surface wind patterns and generates localized pressure drops. These turbulent wind shifts create unpredictable dust devils spinning thermal whirlwinds that travel across the landscape, depositing thick dust layers on optical sensors, scouring surface coatings with abrasive grit, and creating sudden mechanical stress loads on standing antenna masts and solar tracking arrays. Earth shields life from the lethal radiation environment of space through two magnificent natural barriers: a dense atmosphere that absorbs high-energy photons and particles, and a powerful intrinsic magnetic field generated by the churning liquid iron dynamo in its outer core. This geomagnetic bubble, the magnetosphere, deflects the continuous torrent of solar wind and high-energy cosmic rays, creating a protected haven where biological organisms have evolved safely for billions of years. Mars, however, possesses neither of these protective shields. Roughly 4 billion years ago, as the smaller red planet cooled rapidly, its interior dynamo froze, shutting down its global magnetic field. Shortly thereafter, deprived of magnetic protection, the Martian atmosphere was relentlessly stripped away by solar wind, leaving behind a thin, wispy envelope with a surface pressure less than 1% of Earth's. For human pioneers attempting to establish a permanent presence on Mars, this double absence creates a severe biological hazard. The Martian surface is exposed to two distinct forms of ionizing radiation: solar particle events, SPEs, and galactic cosmic rays, GCRs. Solar particle events consist primarily of high-energy protons ejected during violent solar flares and coronal mass ejections. SPEs are episodic, intense, and directionally focused. While a sudden solar flare can deliver a lethal dose of radiation to an unshielded astronaut on the surface within hours, SPEs can be mitigated relatively easily by constructing thick underground storm shelters or piling several meters of regolith atop habitat modules, allowing crew members to take shelter until the solar storm passes. The far more dangerous and intractable threat comes from galactic cosmic rays. Originating outside our solar system from supernova explosions, active galactic nuclei, and cataclysmic cosmic events. GCRs consist of highly energetic atomic nuclei, ranging from single protons to heavy, fully ionized iron nuclei known as HC-Z, and energy particles accelerated to near the speed of light. Because of their immense kinetic energy, GCRs penetrate deeply into matter, striking anything in their path with relentless continuous force. Unlike solar flares, which occur intermittently, galactic cosmic rays wash over Mars in a steady, omnidirectional background stream that never stops. When a high-energy iron nucleus traveling at 90% of the speed of light strikes human tissue, it acts like a microscopic cannonball. It rips through cell membranes, pierces cell nuclei, and shatters double-stranded DNA molecules along its track, leaving a path of dense ionization that cellular repair mechanisms are completely ill-equipped to fix. Over extended periods of exposure, this continuous cellular damage leads to severe biological degradation exponentially elevated cancer risks, degenerative cardiovascular disease, cataracts, immune system suppression, and irreversible central nervous system damage that impairs memory, spatial cognition, and decision-making capabilities in crew members. The obvious engineering solution to radiation is shielding surrounding habitats with thick layers of material to absorb incoming particles. However, when dealing with galactic cosmic rays, physics introduces a terrifying counterintuitive phenomenon known as secondary neutron spallation. When a super-energetic heavy cosmic ray hits a thick shield made of dense materials like lead, steel, or aluminum, it does not simply stop. Instead, the cosmic ray impacts the atomic nuclei of the shielding material itself, shattering those target nuclei into a cascade of high-energy secondary particles, including neutrons, protons, and gamma-ray photons. This secondary particle shower scatters throughout the interior of the habitat. If a shield is not thick enough, or if it is constructed from the wrong materials, it actually increases the total radiation dose experienced by human occupants compared to standing unshielded in open space. The dense metal walls of a spacecraft or habitat can transform a single incoming heavy cosmic ray into a shower of hundreds of secondary neutrons that bounce around inside living quarters, penetrating deep into human organs. To effectively slow down and absorb these secondary neutrons, shielding materials must be rich in low atomic mass atoms, specifically hydrogen, which can absorb neutron kinetic energy through elastic collisions, much like billiard balls colliding with balls of equal mass. This nuclear requirement imposes immense mass penalties on habitat design. Effective GCR shielding requires several meters of water, polyethylene plastic, or liquid hydrogen surrounding every living quarter, or bearing habitats beneath 3 to 5 meters of compacted Martian regolith. While bearing habitats under meters of dirt solves the primary radiation problem for sleeping quarters and work bays, it transforms human life on Mars into a subterranean existence. Pioneers will not live in bright, transparent glass domes looking out over red horizons. They will live in dark, windowless underground bunkers, emerging onto the surface only when necessary inside heavy, awkward spacesuits. Furthermore, subterranean living does not eliminate radiation exposure during surface operations. Every hour spent outside performing construction, mining water ice, maintaining solar fields, or operating rovers accumulates lifetime radiation doses. Current space agency career radiation limits are designed for professional astronauts who spend months on the International Space Station before returning to Earth's protective environment to recover. On Mars, where individuals will live for decades or lifetimes, cumulative radiation doses will inevitably exceed established safety thresholds, leading to premature health decline among the pioneer population. Consider also the biological impact on human reproduction. For a colony to become truly permanent and self-sustaining, it must be able to reproduce gestating, birthing, and raising healthy children across generations without relying on continuous immigration from Earth. Yet, we have zero scientific data on how ionizing radiation impacts mammalian embryonic development, gamete viability, or genetic mutation rates over multiple generations in a low-gravity, high-radiation environment. High-energy cosmic rays striking developing embryos could cause high rates of spontaneous miscarriage, severe birth defects, and inherited genetic mutations that accumulate across generations, threatening the long-term biological viability of the colony. Thus, radiation on Mars is not a minor environmental inconvenience that can be solved with a simple medical pill or a thin sheet of lead. It is an ambient nuclear storm that relentlessly attacks the molecular foundation of human life. It limits surface operational hours, dictates habitat architecture, demands colossal mass budgets for shielding, degrades human cognitive performance, elevates chronic disease rates, and threatens the genetic future of multi-generational settlement. A Mars colony will find itself physically constrained by an invisible nuclear ceiling. The effort required to protect human bodies from continuous galactic cosmic rays will consume a massive fraction of the colony's energy and industrial output. If shielding systems fail, or if colonists spend too much time on the surface attempting to build infrastructure, the slow, relentless accumulation of biological damage will degrade the physical and mental capacity of the population, leaving a weakened, sickened crew unable to maintain the very machines required to keep them alive. To further understand the physics of secondary radiation, consider the composition of a local Martian regolith used for shielding. While dirt is abundant on Mars, raw regolith contains significant fractions of heavy elements such as iron, titanium, and silicon, which generate high secondary neutron yields when struck by primary cosmic rays. To build safe habitat shielding out of local soil, colonists must either process regolith to extract hydrogen-rich clays, or construct massive earthen mounds far thicker than initially calculated, increasing civil engineering workloads on the surface. Furthermore, solar activity modulates the cosmic ray environment in complex ways. During solar maximum, the Sun's expanded magnetic field deflects a larger fraction of galactic cosmic rays away from the inner solar system, slightly reducing background GCR doses on Mars while increasing the frequency of acute solar particle events. During solar minimum, the weakened solar magnetic field allows GCR fluxes to reach peak intensity. Human survival strategies must therefore adapt continuously to an 11-year solar cycle that alternates between acute lethal flare hazards and maximum chronic cosmic ray damage. Moreover, solar particle events during orbital transit and surface operations impose severe acute medical risks. While chronic galactic cosmic rays cause long-term cellular degradation, an unshielded encounter with a major solar proton event delivers several grays of ionizing radiation over a few hours, inducing acute radiation syndrome ARS. Symptoms include severe nausea, vomiting, bone marrow suppression, immune system collapse, and acute gastrointestinal damage. If astronauts working on the Martian surface fail to reach a shielded storm shelter within minutes of a solar flare warning, acute radiation sickness will incapacitate crew members, preventing them from performing critical habitat maintenance and requiring intensive medical care that will overwhelm the colony's small medical facility. Managing acute solar radiation casualties alongside ongoing chronic cosmic ray exposure creates a double biological burden that severely degrades operational safety across the outpost. Human biology is an exquisite product of terrestrial evolution. For over 3.5 billion years, every biological system on Earth, from simple single-celled organisms to complex mammalian bodies, has evolved under the constant, unyielding pull of Earth's gravity, a uniform acceleration of 9.8 meters per second squared, defined as 1 gravity, or 1G, our cardiovascular system, our skeletal structure, our muscular network, our inner ear balance mechanisms, and even the fluid dynamics inside our individual cells are fine-tuned to function within this specific gravitational environment. Mars, however, possesses a surface gravity of only 38% of Earth's roughly 0.38 G. When humans settle on Mars, they enter a biological experiment for which evolution has provided zero preparation. We possess extensive medical data on how the human body responds to microgravity, the near-zero-G environment experienced aboard the Space Shuttle, Mir, and the International Space Station. Decades of space medicine research have revealed that prolonged microgravity causes rapid, destructive physiological degradation. Without the constant load of 1G, astronauts lose up to 1.5% of their bone mineral density every single month, particularly in weight-bearing bones like the pelvis and lower spine. Muscles atrophy rapidly. The cardiovascular system shrinks as blood volume decreases and the heart muscle shrinks, and fluid shifts toward the head cause spaceflight-associated neuroocular syndrome SANS, which flattens eyeballs, swells optic nerves, and permanently impairs vision. To counteract this microgravity decay, astronauts on the International Space Station must exercise for more than 2 hours every day using heavy resistance equipment and treadmills, while taking specialized medications to slow bone resorption. Yet, even with these intense exercise protocols, returning astronauts often struggle to stand upright, experience severe balance disorientation, and require months of physical rehabilitation to rebuild lost bone and muscle mass. Microgravity is not a neutral physical state. It is a slow, relentless biological poison that degrades the human body from the moment weightlessness begins. The critical, unanswered scientific question for Mars settlement is whether partial gravity, specifically the 0.38 g of Mars, is sufficient to prevent this physiological collapse over long periods. We have zero long-term medical data on human or mammalian physiology under 0.38 g. There are no space stations operating at partial gravity, no long-term lunar bases, and no laboratory centrifuges on Earth that can simulate partial gravity for months or years. We simply do not know if 0.38 g sits above or below the physiological threshold required to maintain normal human bone density, cardiovascular health, muscle mass, and cellular function across years of exposure. If 0.38 g lies below the threshold for biological stability, colonists on Mars will undergo continuous, irreversible physiological decay, even if bone mineral loss occurs at only a fraction of the rate seen in microgravity. Over a decade of residence on Mars, colonists will lose a massive percentage of their skeletal mass. Their bones will become fragile and brittle, susceptible to fractures from minor physical impacts. Their cardiovascular systems will adapt to the reduced workload of pumping blood against lower gravity, causing the heart muscle to shrink and blood pressure regulation to degrade. If a colonist who has lived on Mars for 5 years attempts to return to Earth, the sudden return to 1g gravity would crush their weakened skeleton, collapse their circulatory system, and induce immediate cardiovascular shock. This physiological adaptation introduces a terrifying one-way biological trap. After living on Mars for several years, a human may become permanently biologically altered, physically incapable of ever returning to Earth. They would be marooned on the red planet not by a lack of rockets, but by their own weakened biology. Their body would no longer be capable of surviving the 1g environment in which their ancestors evolved. They would belong to Mars biologically, trapped in an environment that is simultaneously destroying their health over long baselines. The biological challenge grows exponentially worse when considering mammalian reproduction and child development. A permanent colony cannot rely forever on adult immigrants from Earth. It must be able to conceive, gestate, birth, and to raise healthy children across generations. Yet, embryonic development is a delicate process governed by precise physical gradients, mechanical cell signaling, and gravitational cues. During early embryonic development on Earth, gravity guides cell migration, body axis orientation, and organ tissue differentiation. We do not know if a human fetus can develop normally inside a mother's womb under 0.38 g. Partial gravity may disrupt fluid distribution in embryonic tissues, cause structural malformations in developing hearts and brains, or impair the formation of the fetal skeleton. Furthermore, birthing a child in partial gravity presents severe medical risks to a mother whose pelvic bones have already been weakened by years of mineral loss. If human reproduction under 0.38 g results in high rates of developmental defects, stillbirths, or maternal mortality, the dream of a self-sustaining human population on Mars dissolves instantly. Consider also the physical development of children raised in Martian gravity. A child born and raised under 0.38 g will grow tall, thin, and slender, with a skeletal structure and muscular system designed specifically for Mars' weak gravitational pull. Their heart will be smaller, their lung capacity adapted to thin internal habitat atmospheres, and their bone density significantly lower than that of an Earth-born human. This first generation of native Martians will be alien to their home planet, physically incapable of ever visiting the birthplace of their species. forever confined to the low-gravity world of their birth. Furthermore, cellular mechanisms themselves may degrade under long-term partial gravity. Recent laboratory experiments with single cells in simulated microgravity reveal disruptions in gene expression, altered protein synthesis, impaired immune cell activation, and abnormal cell division. White blood cells become sluggish, weakening the body's ability to fight off bacterial infections or suppress cancerous cell mutations. Combined with the continuous background radiation environment on Mars, this immune suppression creates a physiological disaster. Colonists will face elevated cancer risks while possessing a weakened immune system, less capable of destroying malignant cells. Thus, the low-gravity barrier represents a fundamental biological constraint that engineering cannot easily fix. You cannot spin an entire planet to increase its gravity. While artificial gravity centrifuges could be built inside habitat modules for sleeping quarters, spending 8 hours a day in a spinning centrifuge creates severe inner-ear vestibular conflict, motion sickness, and structural engineering headaches, while doing nothing for the 16 hours spent working in 0.38 g. Mars gravity is an unalterable planetary parameter. If human biology requires at least 0.5 g or 0.7 g to maintain long-term physiological health and normal reproduction, then Mars is not a new home for humanity. It is a biological dead end. A colony established there would face a quiet generational crisis, a population of aging, brittle-boned pioneers unable to return to Earth, struggling to raise healthy children, and watching their physical vitality slowly drain away into the cold red dirt. To further understand physiological adaptation under partial gravity, consider the ocular impacts observed in long-duration spaceflight. Spaceflight-associated neuroocular syndrome, SANS, occurs when fluids shift toward the head, increasing intracranial pressure and compressing the posterior globe of the eye. On Mars, if 0.38 g is insufficient to maintain normal venous fluid drainage toward the lower body, colonists will suffer chronic intracranial pressure, leading to progressive optic nerve swelling, cotton wool spots on the retina, and irreversible farsightedness that impairs their ability to perform technical maintenance and medical tasks. Furthermore, muscle fiber conversion under reduced gravity presents major operational liabilities. In 1G, human leg and back muscles rely on slow twitch, fatigue-resistant muscle fibers to maintain posture against gravity. In reduced gravity, these slow twitch fibers rapidly convert into fast twitch, easily fatigued fibers, causing colonists to experience rapid muscular exhaustion during routine physical tasks, lowering labor efficiency across the colony's industrial operations. Additionally, neurovestibular adaptation under partial gravity presents persistent operational hazards. The human inner ear relies on otolith organs, tiny calcium carbonate crystals resting on sensory hair cells, to detect gravitational acceleration and vertical orientation. In 0.38 g, the reduced mechanical gravitational load on otolith organs causes persistent sensory conflict between visual inputs, proprioceptive feedback from joint receptors, and inner ear signals. This chronic vestibular mismatch leads to persistent space motion sickness, spatial disorientation, impaired hand-eye coordination, and illusionary sensations of tilting or tumbling during movement. For colonists operating heavy mining machinery, piloting landing vehicles, or conducting delicate EVA construction tasks, chronic spatial disorientation increases error rates and accidental injuries, lowering overall labor efficiency and increasing risk across surface operations. In science fiction depictions of space settlement, human habitats are often shown as serene, self-contained ecological paradises. We envision vast glass-domed cities filled with lush green crops, cascading waterfalls, pristine air, and balanced ecosystems where human waste is magically converted into rich soil and fresh food. This romantic vision relies on a profound misunderstanding of biological thermodynamics. On Earth, We live inside a colossal self-regulating biosphere that has evolved over 4 billion years. The Earth's atmosphere, oceans, rock cycles, and global microbial networks form an immensely resilient life support system powered by a continuous, overwhelming flux of solar energy. When we attempt to replicate this biosphere inside a mechanical habitat on Mars, we step out of natural ecological balance and into the unforgiving laws of thermodynamics and entropy. A Martian habitat is an artificial closed loop, a sealed vessel that must continuously recycle oxygen, water, carbon dioxide, nitrogen, and organic nutrients to keep human occupants alive. In physics, any closed system that attempts to recycle matter and energy is subject to the second law of thermodynamics: entropy always increases. Mechanical components wear down, chemical catalysts become poisoned, biological cultures mutate or die, and trace contaminants accumulate. A closed-loop life support system is not a static machine that runs forever. It is a complex, unstable system that naturally degrades toward disorder, requiring continuous inputs of high-grade energy, specialized maintenance, and external spare parts to prevent lethal failure. Consider the current state of space life support technology. The Environmental Control and Life Support System ECLSSS aboard the International Space Station represents the absolute pinnacle of human bioengineering. It recycles roughly 98% of water from astronaut urine, sweat, and breath condensate, and recovers about 85% of oxygen from exhaled carbon dioxide using Sabatier reactors and electrolysis units. Yet, despite decades of continuous optimization and billions of dollars in development, the ISS life support system is notoriously delicate, frequently breaking down, clogging, and requiring constant intervention by astronauts and ground engineers. Crucially, the ISS ECLSS is not a truly closed loop. It is a partially open loop that relies on frequent resupply missions from Earth to deliver fresh water tanks, nitrogen high-pressure gas resupply, toxic chemical scrubbers, new filtration membranes, and replacement pumps. On Mars, where resupply ships arrive only once every 2 years, life support hardware cannot rely on a terrestrial supply chain. If a Sabatier reactor catalyst becomes contaminated by trace sulfur gases, or if a water distillation assembly scale builds up beyond the capacity of on-site acid, washes to clean, the efficiency of the entire recycling loop drops. A drop in water recycling efficiency from 98% to 90% sounds small, but over a 2-year operational window for a crew of 100, that 8% deficit requires importing or extracting dozens of additional tons of pure water just to make up the shortfall. The biological components of a Martian closed loop introduce even greater instability. To reduce dependence on imported dry food, a Mars colony must grow its own crops using hydroponic or aeroponic systems inside pressurized greenhouses. However, plants are not mechanical machines with predictable operational lifespans. They are sensitive biological organisms vulnerable to disease, light variations, nutrient imbalances, and atmospheric contamination. If a fungal spore or bacterial pathogen enters a habitat's hydroponic bays, it can sweep through monoculture crop beds in days, destroying a colony's entire food supply. Furthermore, plant-based life support requires precise atmospheric balances. Crops consume carbon dioxide and release oxygen during photosynthesis, while human crew members consume oxygen and release carbon dioxide. Balancing these two biological rates inside a small, enclosed atmosphere requires extreme control. If plant growth slows due to a lighting failure or disease, carbon dioxide levels inside the habitat will rapidly climb to toxic levels, while oxygen levels drop. Conversely, if plant growth surges unexpectedly, oxygen concentrations can rise to dangerous levels, transforming the interior habitat atmosphere into a hyper-flammable fire hazard, where a single electrical spark could trigger an uncontrollable blaze. The unseen danger in closed-loop systems is the buildup of volatile organic compounds, VOCs, and trace contaminants. In an open environment like Earth, toxic gases released by plastics, electronics, cleaning agents, human digestion, and off-gassing materials are diluted by billions of cubic kilometers of atmosphere and broken down by solar ultraviolet light. Inside a sealed Martian habitat, these trace gases accumulate continuously. Trace amounts of formaldehyde, benzene, ammonia, carbon monoxide, and siloxanes off-gas from habitat walls, electrical wiring, human skin, and sanitation chemicals. If catalytic oxidizers and trace contaminant control subsystems fail to scrub these volatile compounds continuously, they build up to toxic concentrations, causing chronic headaches, respiratory irritation, cognitive decline, and organ damage among the crew. Scrubbing these trace toxins requires specialized chemical beds such as activated charcoal, lithium hydroxide, and noble metal catalysts, which themselves have finite operational lifespans and must be regenerated or replaced using energy-intensive chemical processes. Consider also the microbial nightmare of an enclosed habitat. Human bodies harbor trillions of bacteria, fungi, and viruses, which are continuously shed into the habitat environment in a sealed, warm, humid environment with recycled air and water. Opportunistic microbes flourish on damp surfaces, inside water recycling conduits, and within air filtration ducts. Without natural ecological competition from outdoor soil microbes, a small number of dominant, potentially mutated bacterial strains can form resilient biofilms inside water pipes, clogging filters, corroding metal fittings, and contaminating drinking water supplies with endotoxins. This biological degradation creates a terrifying feedback loop. As mechanical recycling systems degrade, water purity drops and air filtration efficiency decreases. Crew members operating under physiological stress from radiation and low gravity become more susceptible to infections from opportunistic habitat microbes. Sick crew members require more medical care, produce more metabolic waste, and are less capable of performing the arduous physical maintenance required to fix the failing life support hardware, accelerating the overall decline of the habitat ecosystem. Thus, closed-loop thermodynamics represents a continuous battle against environmental entropy. A life support system is not a permanent piece of infrastructure like a concrete building. It is a high-maintenance biological and mechanical engine that requires absolute perfection to avoid disaster. A single uncorrected chemical imbalance, a single persistent mechanical failure, or a single agricultural disease outbreak can trigger a cascading collapse across the entire habitat. A Mars colony will find itself trapped in an endless cycle of life support firefighting. Colonists will spend a massive fraction of their waking hours monitoring sensor outputs, cleaning clogged distillation units, replacing poisoned catalyst beds, scrubbing mold from habitat walls, and trying to keep delicate crops alive. Over years of operation, as spare parts run low and chemical reagents are depleted, the closed loop will gradually loosen, leaking vital gases, accumulating toxins, and slowly poisoning the very humans it was built to protect. To further illustrate the thermodynamic limits of life support systems, consider the energetic cost of atmospheric scrubbing. Removing carbon dioxide from habitat air requires passing high-volume airflow through regenerative amine beds or zeolites. These materials must be periodically heated to high temperatures to desorb the trapped gas and vent it to processing reactors. This thermal regeneration cycle consumes colossal amounts of electrical energy, creating a major power tax on habitat generators that persists regardless of whether the colony is producing useful economic output or simply trying to keep its occupants from suffocating. Furthermore, nitrogen management presents a silent operational threat. Earth's atmosphere is 78% nitrogen, providing an inert buffer gas that prevents oxygen fires and maintains atmospheric pressure. On Mars, where atmospheric pressure is low, and nitrogen makes up only a small fraction of the thin ambient gas. leaking habitat air must be replenished with imported or locally extracted nitrogen. If nitrogen extraction plants fail, habitat operators will be forced to lower overall pressure or increase oxygen fractions, escalating fire risks and accelerating oxygen toxicity among the crew. Furthermore, trace contaminant scrubbing in closed-loop systems requires complex chemical regeneration infrastructure. Activated charcoal beds used to adsorb heavy volatile organic compounds must be periodically thermal desorbed, using high-temperature vacuum ovens, venting trapped toxins into specialized waste containment or space vacuum. Noble metal catalytic oxidizers operating at hundreds of degrees Celsius require continuous electrical power to break down methane, carbon monoxide, and formaldehydes into carbon dioxide and water vapor. If heater elements fail or thermal insulation degrades, catalytic oxidizers drop below operating temperatures, allowing toxic trace gases to pass through unscrubbed and circulate throughout the habitat air distribution network. Maintaining these high-temperature chemical scrubbers requires continuous monitoring, specialized heating elements, and spare catalyst beds, adding another layer of energy and mechanical overhead to the colony's life support operations. The primary pillar of modern Mars colonization plans is the concept of in situ resource utilization, or ESRU. Proponents argue that a Mars colony will not need to import its basic industrial consumables from Earth, because Mars possesses vast natural reserves of raw materials. The red planet has an atmosphere composed of 95% carbon dioxide, vast deposits of subsurface water ice, and a surface covered in iron-rich basaltic regolith. Under the ESRU paradigm, automated industrial units will harvest Martian atmospheric gas and subsurface ice, combining them via the Sabatier reaction and electrolysis to produce liquid methane fuel and pure liquid oxygen for return rockets, while extracting drinking water, breathable air, and agricultural inputs for human habitats. On paper, ESRU is an extraordinarily elegant concept. It turns Mars from a barren void into a cosmic gas station, dramatically reducing the mass that must be launched from Earth. However, when one transitions from high-level architectural concepts to the physical reality of heavy industrial processing on the Martian surface, the ESRU paradigm reveals a terrifying energy and machinery deficit. In situ resource utilization is not a free biological gift from the planet. It is an incredibly energy-intensive, highly complex industrial process that requires massive capital equipment, continuous heavy maintenance, and extraordinary power budgets to produce even modest amounts of usable material. Consider the physical reality of extracting water ice on Mars. While orbital satellite radar data confirms the existence of vast underground ice sheets on Mars, this ice is not sitting in convenient open lakes or soft-surface glaciers near the warm equator. The vast majority of accessible water ice is locked beneath meters of rock-hard, frozen permafrost and rocky overburden in the cold high latitudes, where surface temperatures drop below -100 degrees Celsius. Extracting this subsurface ice requires heavy industrial mining equipment, automated drilling rigs, heavy excavators, rock crushers, and thermal melting systems capable of operating in extreme cold, abrasive dust, and near vacuum conditions. Mining frozen permafrost on Mars is an operational nightmare. The frozen ground a concrete-like mixture of basaltic rock, fine dust, and solid ice is exceptionally hard, wearing down drill bits, excavator teeth, and hydraulic seals at extreme rates. Once the ice-bearing regolith is excavated, it must be transported to sealed processing reactors and heated to high temperatures to melt the ice and vaporize the water, separating it from toxic perchlorate, fine silt, and heavy metals. The thermal energy required to vaporize water ice, the density variation is less than 0.004. The density variation is less than 0.004 megajoules per kilogram combined with the mechanical energy required to mine frozen ground creates an enormous energy debt for every litre of pure water produced. The energy arithmetic grows even more daunting when calculating rocket propellant production. To manufacture the fuel required for a single heavy return rocket, typically several hundred tons of liquid methane and liquid oxygen, an ECSRU facility must process thousands of tons of atmospheric carbon dioxide and extract hundreds of tons of pure water ice. Operating the Sabatier reactors, electrolysis units, gas compressors, and cryogenic refrigeration systems needed to liquefy and store methane at minus 161 degrees Celsius and oxygen at minus 183 degrees Celsius requires megawatt-scale electrical power, operating continuously for months. Where will this massive electrical power come from? Space architects typically propose two power sources: solar photovoltaic arrays or surface nuclear reactors. Solar power on Mars, however, suffers from severe physical limitations. Mars sits 50% further from the Sun than Earth does, reducing incoming solar irradiance by more than 55%, to an average of only 590 watts per square meter. Furthermore, atmospheric dust scattering, low sun angles, and global dust storms that can obscure the sky for months make solar power an unreliable baseline for heavy industrial processing. To provide a continuous megawatt of electrical power using solar energy, a colony would need to deploy tens of thousands of square meters of solar panels, along with massive utility-scale battery systems weighing hundreds of tons to store energy through the cold 16-hour Martian night. Deploying, clearing dust from, and maintaining square kilometers of delicate solar arrays on a dusty, wind-swept terrain is an immense physical workload that would consume a major fraction of a colony's robotic and human labor force. This leaves nuclear power as the only physically viable option for heavy ISRU operations. Compact kilopower or megawatt-scale fission reactors, fueled by enriched uranium, can operate continuously regardless of dust storms, day-night cycles, or latitude. However, deploying nuclear reactors on Mars introduces severe engineering hurdles. Nuclear reactors require massive cooling radiators to reject waste heat into the thin Martian atmosphere. Because the Martian atmosphere is extremely sparse, convective cooling is nearly non-existent, forcing reactors to rely almost entirely on thermal radiation. Radiators for a megawatt-scale nuclear plant must span thousands of square meters, creating massive physical structures vulnerable to micrometeorite impacts and dust contamination. The core illusion of ISRU is that it solves the resource problem without creating a machinery trap. To harvest water and make fuel, you need heavy mining rigs, chemical reactors, cryo-coolers, and nuclear power plants. But who manufactures the spare parts for the heavy mining rigs when their hardened steel teeth wear out against frozen basalt? Who replaces the high-pressure seals inside the Sabatier reactors when they degrade under thermal cycling? Who fabricates new cryogenic valves when fine dust scores their mating surfaces? ISRU creates a circular dependency. You need complex industrial machinery to harvest local resources, but to keep that industrial machinery running, you need an even larger industrial supply chain to manufacture replacement parts, lubricants, chemical reagents, and electrical components. If a colony cannot manufacture precision replacement parts locally out of Martian rocks, its ISRU facilities will gradually break down, component by component. The moment a critical compressor pump or electrical inverter fails in the fuel plant, the entire resource chain grinds to a halt. Thus, the ISRU paradigm is not a simple shortcut to planetary independence. It is a high-stakes engineering gamble. It exchanges a heavy payload penalty on Earth for an immense industrial maintenance burden on Mars. If the local industrial infrastructure falls behind on its maintenance cycles, or if power generation systems suffer degradation, the resource miracle evaporates. A Mars colony will find itself trapped in an energy and maintenance deficit. Pioneers will spend so much energy and time simply keeping their water extraction rigs and power plants operating that they will have little capacity left for expansion, scientific research, or building secondary industries. The resource wealth of Mars will remain locked beneath the frozen red soil, just out of reach of a colony whose machines are slowly grinding themselves to dust. To further evaluate the energetic limits of ISRU, consider the cryogenic storage requirements for harvested propellants. Liquid methane and liquid oxygen must be maintained at ultra-low cryogenic temperatures inside massive storage tanks for months prior to the arrival of return vehicles. In the thin Martian atmosphere, solar thermal radiation during the day heats tank surfaces, causing cryogenic boil-off where precious refined propellants vaporize and vent into space. Preventing boil-off requires continuous, power-hungry active refrigeration systems, turning every gallon of stored fuel into an ongoing electrical tax on the colony's central power grid. Furthermore, chemical processing of Martian atmospheric gas introduces catalyst poisoning risks. The Martian atmosphere contains trace amounts of sulfur dioxide, argon, nitrogen, and carbon monoxide. As atmospheric compressors feed raw carbon dioxide into Sabatier reactors, trace sulfur compounds rapidly poison nickel and ruthenium catalyst beds, degrading methane conversion rates. Filtering atmospheric gas to ultra-high purity prior to chemical processing requires complex molecular sieve beds that must themselves be periodically baked out and regenerated, adding another layer of mechanical complexity to the ISRU chain. Moreover, cryogenic fluid management on the Martian surface presents severe long-term storage challenges. Liquid methane and liquid oxygen must be stored inside large insulated tanks at temperatures below -160 degrees Celsius. In the low-density carbon dioxide atmosphere of Mars, boil-off occurs due to thermal radiation from the warm surface during the day and conductive heat transfer through structural tank supports. To prevent continuous fuel loss, storage tanks must utilize active cryocoolers operating on reverse Brayton or pulse tube thermodynamic cycles, consuming significant electrical power. If power generation systems experience dust-induced output drops or mechanical faults, active cooling shuts down, causing internal tank pressures to rise as cryogens boil. Operators must then vent precious refined propellants into the atmosphere to prevent tank overpressurization, destroying months of hard-won propellant production in days. When space agencies and private aerospace companies design missions to Mars, their engineering blueprints are filled with exquisite mathematical detail. Life support flow rates, trajectory delta-V budgets, structural stress tolerances, and electrical power curves are calculated to decimal precision. Yet, embedded inside these complex mechanical systems is a nonlinear, unpredictable biological component that defies simple mathematical modeling the human mind. A Mars colony is not just a technological facility, it is an intense psychological pressure vessel, an artificial, claustrophobic environment where small groups of human beings must live and work together under extreme stress, complete physical isolation, and zero possibility of escape for years or decades. To understand the unique psychological crucible of a Mars outpost, one must examine the sensory and environmental deprivation inherent to habitat life. On Earth, human mental health is sustained by a continuous unconscious stream of natural sensory inputs, the vast open expanse of the sky. Changing weather patterns, shifting sunlight, green vegetation, natural odors, the sound of flowing water, and the freedom to walk outside without wearing a pressurized survival suit. On Mars, this rich terrestrial sensory tapestry is replaced by absolute, artificial monotony. Colonists will live inside buried subterranean bunkers or pressurized metal modules, breathing recirculated air that smells of machine oil and chemical scrubbers, listening to the continuous background hum of life support fans, and working under artificial LED lighting. This sensory deprivation is compounded by severe spatial confinement. A small pioneer population will spend months and years cooped up inside pressurized volumes smaller than a modest suburban home, sharing cramped sleeping quarters, communal mess halls, and narrow hygiene bays. There are no private outdoor spaces to retreat to. no long walks through open countryside to clear one's head after argument, and no option to leave the facility. Every social interaction, whether with colleagues, superiors, or romantic partners, occurs under the intense gaze of a tiny, enclosed community. Over time, minor personal quirks, communication differences, and habitual annoyances that would be trivial on Earth magnify into intense interpersonal friction. The psychological pressure is further intensified by the terrifying reality of communication latency. Mars resides at distances ranging from 55 million to over 400 million kilometers from Earth, depending on their relative orbital positions. Because radio signals travel at the speed of light, two-way communication between Earth and Mars experiences an unavoidable speed of light delay ranging from 4 minutes to more than 24 minutes each way. A simple question sent to Earth requires waiting up to 48 minutes for an answer to return. This communication lag permanently severs real-time human connection with the home planet. Colonists cannot have spontaneous phone calls with family members, real-time therapy sessions with psychologists, or live video conversations with friends. Every message must be recorded as an asynchronous audio or video file, sent across the cosmic gulf, and waited on for tens of minutes. This delay creates a profound sense of psychological alienation. Over time, colonists will realize that Earth is no longer a real-time presence in their lives. It becomes a distant, slow-moving archive that sends delayed video clips and news feeds. The emotional ties that bind individuals to terrestrial society will gradually stretch and weaken, leaving the crew psychologically marooned in the deep void. Furthermore, communication latency severely alters operational command structures. During early mission phases, mission control on Earth will attempt to manage habitat procedures, safety protocols, and operational schedules down to the minute, just as they do on the International Space Station. But when an operational crisis occurs on Mars, a life support alarm, a water pump failure, or a habitat leak, a crew cannot wait 48 minutes for ground controllers to review telemetry data and issue commands. The crew on Mars must make split-second life or death decisions independently. This operational autonomy inevitably leads to conflict between the colony and ground controllers on Earth. Historical precedents from long-duration terrestrial isolation experiments, such as Antarctic winter overstations, submarine deployments, and the famous Skylab 4 mutiny in 1973, demonstrate that isolated crews under high stress frequently develop us versus them group dynamics. They project their frustration, exhaustion, and anxiety onto ground controllers whom they perceive as out-of-touch micromanagers sitting safely on Earth. On Mars, where ground controllers are separated by 20 minutes of light travel time and cannot intervene physically. This psychological rift can lead to non-compliance, defiance of safety directives, and complete breakdown of organizational command. Consider also the psychological impact of sleep disruption and chronic cognitive fatigue. Living in an environment with no natural daylight cycles, constant background machine noise, high ambient carbon dioxide levels, and continuous low-dose radiation exposure severely disrupts human circadian rhythms. Chronic insomnia, altered sleep architecture, and elevated stress hormone levels impair executive function, emotional regulation, memory consolidation, and reaction times. In a high-risk operational environment where a single misread valve gauge or an incorrectly entered keyboard command can depressurize a module and kill the entire crew, chronic cognitive fatigue is a lethal hazard. The psychological strain becomes even more volatile when personal conflicts arise within small, isolated crews. On a long-duration mission where individuals cannot leave, interpersonal disputes over workload distribution, romantic rivalries, leadership styles, or safety compliance can polarize a small community. In extreme cases, depression, severe anxiety, paranoid delusions, or overt hostility could emerge within the crew. If a colonist suffers a severe psychiatric breakdown or becomes violently non-compliant, a Mars base lacks specialized psychiatric facilities, medical isolation wards, or law enforcement mechanisms. A single unstable individual inside a fragile pressurized habitat threatens the safety of everyone. Thus, the human mind represents a fragile, non-deterministic point of failure in space settlement. We can build radiation shields out of water tanks, engineer triple-redundant life support pumps, and design heavy rockets that land autonomously on target. But we cannot re-engineer the evolutionary psychology of human beings who evolved to live in open, social, terrestrial environments. A Mars colony will find itself fighting an internal psychological war of attrition. As years turn into decades, the sensory monotony, physical confinement, communication lag, and chronic stress will wear down the mental resilience of even the most carefully screened pioneers. The failure of a red outpost may not be recorded as a mechanical explosion or an oxygen valve failure, but as a quiet human tragedy, a community fractured by isolation, cognitive fatigue, and internal conflict, unable to maintain the absolute discipline required to survive on an unforgiving world. To further understand isolation psychology, consider the phenomenon known as Earth Out of View syndrome. As a spacecraft travels toward Mars, Earth shrinks from a bright blue marble into an insignificant point of light, before disappearing entirely behind the solar glare or habitat walls. Space psychologists predict that losing visual contact with Earth will trigger a unique form of existential dread and derealization never before experienced in human history. Seeing the entire birthplace of humanity vanish into a star field deprives the human mind of its ultimate psychological anchor, inducing severe feelings of cosmic insignificance, abandonment, and existential helplessness. Furthermore, grief management across interplanetary distances introduces severe emotional trauma. During long deployments, colonists will inevitably receive delayed video messages informing them that a parent, spouse, or child on Earth has died, or that a major disaster has struck their hometown. Unable to attend funerals, comfort loved ones, or offer assistance, colonists will be forced to process profound grief while isolated inside a metal bunker, continuing heavy operational routines under severe emotional distress, further accelerating psychological burnout across the crew. Additionally, group decision-making under high isolation and stress is subject to groupthink and psychological polarization. In small, isolated communities cut off from external social diversity, crews naturally develop rigid internal social norms, unspoken taboos, and defensive insularity. Dissenting opinions regarding operational procedures or safety concerns are frequently suppressed to maintain apparent group harmony, leading to flawed decision-making during technical emergencies. Furthermore, severe isolation accelerates psychological burnout among key technical specialists. If the colony's sole chief medical officer or primary life support engineer experiences severe depression, burnout, or emotional withdrawal, the entire community loses vital operational expertise. Cross-training crew members in complex technical disciplines provides partial risk mitigation, but cannot fully replace years of specialized medical or engineering experience, leaving the colony vulnerable to single-point human failures. When proponents of space settlement discuss the colonization of Mars, they often focus on vision, inspiration, and the long-term survival of human consciousness. These are noble, powerful motivations that can rally public enthusiasm and secure initial funding for early exploration missions. However, history teaches us that permanent human settlements are rarely sustained by inspiration alone. Whether examining ancient trade outposts, colonial harbors, or industrial mining towns on Earth, permanent human presence has almost always required a viable economic foundation, a continuous flow of economic value that offsets the massive capital costs required to build and maintain the settlement. When we analyze Mars through the lens of macroeconomics and trade theory, we encounter a fundamental structural vulnerability. A Mars colony represents a profound economic dead end that may never generate positive return on investment for its terrestrial sponsors. To understand the economic bottleneck of Mars colonization, one must examine the cost structure of interplanetary transportation. Transporting material off Earth requires overcoming a deep gravitational well, consuming massive quantities of high-grade aerospace propellants, utilizing multi-billion-dollar launch infrastructure, and operating complex deep space navigation systems. Even under the most optimistic revolutionary projections for fully reusable super-heavy launch vehicles, delivering a single kilogram of cargo to the Martian surface will still cost thousands of dollars. Delivering heavy industrial machinery, habitats, medical supplies, electronics, and replacement parts to Mars requires expenditures that scale into hundreds of billions of dollars per decade. In economic terms, a Mars colony is an extraordinarily expensive importer. Every piece of technology, every spare seal, every chemical reagent, and every medical device delivered from Earth arrives burdened with immense transportation overhead. For a colony to maintain this supply line over decades, it must either be permanently subsidized by terrestrial governments and philanthropic billionaires, or it must develop high-value exports that it can sell back to Earth to pay for its imports. This is where the economic model of Mars completely breaks down. Mars possesses virtually nothing that can be economically exported back to Earth. Consider the potential physical resources of Mars. Proponents sometimes suggest mining rare metals, minerals, or water ice on Mars to sell. But Mars does not possess exotic elements that do not exist on Earth. Platinum, gold, rare earth elements, and industrial metals exist in abundance in Earth's crust and can be mined terrestrially at a tiny fraction of the cost of harvesting them on Mars and shipping them across 400 million kilometers of space. Even if a Martian colony discovered a mountain of pure platinum, the energetic and monetary cost of launching that heavy metal off Mars, transporting it across deep space, and landing it safely on Earth would far exceed the market value of the platinum itself. What about shipping resources to orbital markets or lunar bases, while launching materials off Mars requires less energy than launching off Earth due to Mars's lower gravity? 38G. Asteroids offer a vastly superior source of space resources. Near-Earth asteroids and main-belt asteroids possess zero gravity wells, making it vastly easier and cheaper to extract metals and water ice from asteroids than to mine them on the surface of Mars and launch them out of Mars' gravitational potential well. Mars is too far away and has too deep a gravity well to serve as a competitive resource exporter for the rest of the solar system. This leaves non-physical exports intellectual property, scientific data, software, media, and patentable inventions developed by Martian scientists working in extreme environments. While scientific data from Mars is undeniably valuable for fundamental research, the global market value of scientific data is orders of magnitude smaller than the hundreds of billions of dollars required to maintain the physical infrastructure of a living colony. Earth-based corporations and governments will not spend $50 billion a year on resupply rockets merely to buy scientific research papers or software code that could be generated on Earth for a tiny fraction of the price. This imbalance reveals the core economic reality a Mars colony suffers from a permanent trade deficit that cannot be closed by physical or intellectual exports. It is a one-way financial drain, an immense technological luxury funded entirely by wealth generated on Earth. So long as the home planet remains prosperous, politically stable, and enthusiastic about space exploration, government space agencies or wealthy private visionaries may continue to fund resupply rockets out of national prestige, scientific curiosity, or ideological passion. However, historical economics demonstrates that national prestige and visionary philanthropy are notoriously fragile. Short-lived motivations, government budgets fluctuate with political elections, geopolitical crises, and domestic economic recessions. When a home nation faces pressing terrestrial emergencies such as severe economic downturns, infrastructure degradation, environmental catastrophes, or military conflicts, public and political support for spending billions of dollars resupplying a distant scientific outpost in space evaporates rapidly. Consider the historical precedent of the Apollo program. In the 1960s, the United States spent over 4% of its federal budget to land 12 humans on the moon, driven by intense Cold War geopolitical competition with the Soviet Union. Yet, the moment the political and prestige objectives were achieved, public and congressional support plummeted. The final Apollo missions were cancelled, the production lines were shut down, and humanity did not set foot on the moon again for over half a century. If a lunar program backed by the world's wealthiest superpower could be cancelled almost overnight due to shifting political priorities, a Mars colony requiring continuous multi-billion-dollar subsidies for centuries is extraordinarily vulnerable to economic abandonment. If terrestrial funding dries up and resupply ships stop flying, a Mars colony that has not achieved complete industrial independence cannot survive on its own. As life support components degrade, life-saving medicines expire, microelectronics fail, and mechanical mining equipment breaks down without spare parts, the colony will face a slow, systemic collapse. The outpost will not fail because its scientists lacked brilliance. It will fail because its economic foundation was an artificial construct sustained entirely by wealth generated on a world 400 million kilometers away. Thus, the economic dead end represents a silent structural countdown. A Mars colony is engaged in a race against time. It must achieve total technological and industrial self-sufficiency before Earth grows tired of paying the bill. Given the immense, almost insurmountable industrial threshold required for complete self-sufficiency, the probability that terrestrial funding will fail before that threshold is reached is extraordinarily high. A Mars colony will find itself living on economic borrowed time. Every budget cycle on Earth will represent an existential gamble for the pioneers on the Red Planet. If a global crisis or a shift in political willpower on Earth halts the supply rockets for just a few transfer windows, the colony will be left marooned a high-tech island universe whose economic bridge to reality has been permanently severed. To further illustrate this economic vulnerability, consider the maintenance costs of dedicated launch infrastructure on Earth. Sustaining an interplanetary supply chain requires maintaining massive launch pads, specialized propellant refineries, deep space tracking radar networks, and thousands of aerospace engineers on Earth. These terrestrial support operations represent fixed annual overhead costs running into billions of dollars, regardless of how many rockets are launched per year. If financial crises force operators to decommission launch facilities or lay off technical workforces on Earth, the colony on Mars loses its supply line long before the rockets themselves run out of fuel. Furthermore, intellectual property exports from Mars face severe legal and commercial hurdles. Patents and software developed on Mars must be commercialized inside terrestrial markets, dominated by Earth-based corporations with far greater capital resources and lower operational overhead. A Martian research lab cannot outcompete terrestrial research institutions operating with abundant energy, cheap labor, and direct access to global supply chains, ensuring that the economic value created on Mars remains a tiny drop against its massive financial consumption. Moreover, financial inflation and currency fluctuations on Earth directly impact the long-term sustainability of interplanetary logistics. Subsidizing a Mars colony requires long-term capital commitments spanning decades. If terrestrial economies experience high inflation, currency devaluation, or sovereign debt crises, the real purchasing power of space agency budgets or private endowment funds shrinks significantly. When resupply contracts come up for renewal, aerospace contractors will face elevated manufacturing and propellant costs, forcing governments to reduce mission frequency or cut cargo volumes. A colony operating with zero margin of safety will experience immediate material shortages as resupply ship payloads are trimmed to fit shrinking terrestrial budgets, demonstrating how terrestrial economic instability directly translates into life-threatening supply deficits on Mars. The ultimate dream of space settlement enthusiasts is terraforming the theoretical planetary engineering process of modifying a cold, dead planet's atmosphere, temperature, and surface chemistry to make it hospitable for unshielded human life. In popular culture, documentaries, and speculative science literature, terraforming Mars is presented as a magnificent but achievable long-term engineering project. We are shown visions of massive orbital mirrors focusing sunlight onto the Martian polar caps, nuclear detonations releasing trapped greenhouse gases, and bioengineered cyanobacteria spreading across crimson soil, gradually building a thick, warm carbon dioxide atmosphere over a few centuries, followed eventually by a breathable oxygen sky. This terraforming narrative provides a powerful ideological foundation for Mars colonization. It allows proponents to frame early habitat living not as a permanent subterranean prison sentence, but as a temporary pioneer phase leading toward a green, open sky world where future generations can walk outside without spacesuits. However, when modern planetary science and atmospheric physics are applied to the terraforming concept, the dream dissolves into a physical impossibility. Terraforming Mars is not a challenging engineering problem waiting for future technology. It is a physical illusion blocked by fundamental planetary dynamics and a severe lack of essential raw materials. The primary physical obstacle to terraforming Mars is the planet's severe inventory deficit of volatile gases, specifically carbon dioxide. The density variation is less than 0.004. The density variation is less than 0.004. To warm Mars from its current average temperature of -60 degrees Celsius up to a point where liquid water can exist stably on the surface, the atmosphere must be thickened dramatically. Currently, the Martian surface pressure is roughly 6 millibars less than 1% of Earth's sea level pressure of 1,013 millibars. To produce a greenhouse effect strong enough to warm the surface to habitability, Mars would require a pure carbon dioxide atmosphere with a surface pressure equal to at least 1 to 2 bars over 100 to 200 times more gas than currently exists in the Martian sky. Where would this massive volume of carbon dioxide come from? For decades, space architects assumed that vast quantities of the density variation is less than 0.004. The density variation is less than 0.004 was stored as dry ice in the polar ice caps, or adsorbed into carbon-rich minerals inside the upper regolith, waiting to be released by artificial heating. However, detailed atmospheric and surface measurements conducted by NASA's MAVEN Mars Atmosphere and Volatile Evolution spacecraft and the Mars Reconnaissance Orbiter shattered this assumption. The data revealed that even if humanity were to deploy solar mirrors, detonate thermonuclear weapons over the poles, and heat every accessible square meter of the Martian surface regolith down to depths of several meters, the total recoverable carbon dioxide would add only a tiny fraction to the atmosphere, raising surface pressure from 6 millibars to less than 20 or 30 millibars. This is far below the threshold needed to trigger a self-sustaining greenhouse effect. The volatile inventory required to build a thick atmosphere simply does not exist on Mars. It was lost to space billions of years ago. Why did Mars lose its atmosphere? The answer lies in planetary physics and solar interaction. Roughly 4 billion years ago, as the small core of Mars cooled and solidified, its global magnetic field collapsed, deprived of a protective magnetosphere. The upper atmosphere of Mars was exposed directly to the solar wind, a high-speed stream of charged solar particles. Over billions of years, a process known as unshielded solar wind, stripping and sputtering, gradually eroded the Martian atmosphere, blowing trillions of tons of carbon dioxide, water vapor, and nitrogen out into interplanetary space. MAVEN's instruments directly measured this ongoing atmospheric erosion, confirming that even today, Solar wind continues to strip hundreds of tons of gas from the upper Martian atmosphere every single day. If humanity were somehow able to import trillions of tons of carbon dioxide from icy comets or outer solar system moons to build a temporary atmosphere on Mars, that manufactured atmosphere would immediately begin leaking back out into space, continuously stripped away by solar radiation, unless a planet-sized artificial magnetic shield was deployed at the Sun-Mars L1 Lagrange point, an engineering structure requiring megawatt-scale magnetic field generators far beyond human capabilities. Furthermore, even if a thick carbon dioxide atmosphere could somehow be created, carbon dioxide is not breathable for humans. The density variation is less than 0.004 The density variation is less than 0.004 atmosphere at 1 bar of pressure would be instantly lethal, causing hypercapnia, rapid loss of consciousness, and death within minutes. To make the atmosphere breathable for humans and animal life, the carbon dioxide must be converted into diatomic oxygen. The density variation is less than 0.004. The density variation is less than 0.004 and mixed with a massive buffer gas, specifically nitrogen. The density variation is less than 0.004. The density variation is less than 0.004. On Earth, nitrogen makes up 78% of our atmosphere, acting as an inert buffer that dilutes oxygen to safe levels 21%, preventing spontaneous atmospheric fires and maintaining physiological lung pressure. On Mars, nitrogen is extraordinarily rare, making up only 2.6% of the wispy atmosphere, with zero evidence of massive nitrate mineral beds on the surface. Without trillions of tons of inert nitrogen gas to build an atmospheric buffer, creating a human-breathable open atmosphere on Mars is physically impossible. You cannot fill a planetary atmosphere with pure oxygen without triggering global firestorms that would consume every organic structure on the surface. Consider also the timescales involved in biological terraforming. If cyanobacteria and genetically modified plants were introduced to convert carbon dioxide into oxygen via photosynthesis, the biological conversion process would require tens of thousands to hundreds of thousands of years of unbroken ecological stability. Plants require liquid water, warm temperatures, protection from ultraviolet radiation, and rich organic soils, none of which exist on the surface of Mars today. Expecting biological organisms to build a breathable sky on a frozen, irradiated planet without an atmosphere is a logical impossibility. Thus, the terraforming narrative is a dangerous technological distraction. It presents a sci-fi fantasy that encourages us to view Mars as a future Earth-like paradise, masking the brutal reality that Mars is a permanently dead, airless, frozen rock. Human pioneers will never walk outside on Mars in shorts and t-shirts under a blue sky. They will forever be confined to buried pressure vessels, breathing recycled air, drinking purified urine, and staring out at salmon skies through thick quartz viewports. A Mars colony that bases its long-term survival strategy on the promise of terraforming is building its foundation on a physical lie. When the pioneers realize that the atmosphere cannot be thickened, that the volatile gases do not exist, and that open sky living will never happen, the psychological and ideological justification for enduring the horrors of habitat life will collapse. Mars will be revealed for what it truly is, an unalterable, hostile planetary prison from which technology can offer no ecological escape. To further emphasize atmospheric stripping mechanics, consider photodissociation of water molecules in the upper atmosphere. Solar ultraviolet radiation breaks atmospheric water vapor into hydrogen and oxygen. The light hydrogen gas rapidly ascends to the exosphere, where thermal escape velocities allow it to bleed off into deep space, leaving behind unbound oxygen that reacts with surface rocks to form iron oxides. This ancient photochemical process is precisely why Mars acquired its characteristic red rust color, a silent geological testimony to a planet that bled its oceans into the cosmic void billions of years ago. Furthermore, deploying artificial greenhouse gases such as chlorofluorocarbon CFCs or sulfur hexafluoride, the density variation is less than 0.004 SF6. The density variation is less than 0.004. To warm the surface presents massive industrial hurdles. Synthesizing millions of tons of fluorinated gases on Mars requires abundant fluorine and sulfur resources that are sparsely distributed across the surface, requiring vast chemical processing infrastructure that would consume more energy than the colony could produce across centuries of operation. Furthermore, solar wind stripping of heavy isotopes demonstrates the irreversible nature of Martian atmospheric loss. Isotopic measurements conducted by the Curiosity rover show that Mars' atmosphere is significantly enriched in heavy isotopes of argon. The density variation is less than 0.004. 38R36. The density variation is less than 0.004, and carbon. The density variation is less than 0.004. 13Cs. 12C. The density variation is less than 0.004 compared to Earth. Because lighter isotopes, the density variation is less than 0.004. 36 Mars, the density variation is less than 0.004, and the density variation is less than 0.004. The density variation is less than 0.004 are preferentially knocked into space by solar wind impacts. The current isotopic ratio provides unerased physical proof of ancient atmospheric loss. This isotopic mass fraction confirms that over 90% of Mars' primordial atmosphere was permanently lost to space billions of years ago. The volatile inventory cannot be restored by surface heating or biological activity, confirming that atmospheric loss on Mars is an irreversible planetary evolution that human technology cannot undo. We have examined the terrifying web of physical, biological, thermodynamic, economic, and psychological barriers that stand between humanity and a permanent settlement on Mars. We have seen how the 26-month orbital window creates an unyielding logistical bottleneck, how toxic perchlorates, sharp abrasive dust, and electrostatic adhesion relentlessly attack suits, seals, lungs, and solar arrays, how galactic cosmic rays shatter DNA and generate secondary neutron showers inside metal habitats, how partial gravity threatens long-term skeletal integrity, cardiovascular health, and human reproduction, how closed-loop life support systems naturally degrade toward entropy and toxic contamination, how resource extraction requires energy budgets and spare parts fleets far beyond our industrial capacity, how psychological isolation severs real-time connection with Earth, how severe trade deficits leave outposts vulnerable to political abandonment, and how planetary atmospheric physics renders the dream of terraforming a physical impossibility. When these multi-layered constraints are assembled into a single analytical framework, a profound conclusion becomes inescapable. Mars is not a planet B. The popular modern argument that colonizing Mars is an urgent biological necessity, an essential insurance policy to back up the human species against terrestrial extinction events such as asteroid impacts, nuclear war, supervolcanic eruptions, or runaway climate change is fundamentally flawed. It rests on a deep failure to understand the absolute hostility of the Martian environment compared to even the most catastrophically damaged terrestrial biosphere. Consider the physical reality of Earth after a worst-case global catastrophe. Consider a scenario where a massive 6-mile asteroid strikes Earth, or a global thermonuclear war erupts, or a runaway climate collapse occurs. In any of these horrifying apocalyptic scenarios, the damaged Earth remains vastly more habitable than Mars is on its best day. Even in the aftermath of a nuclear winter or a major impact event, Earth retains a dense atmosphere that blocks lethal cosmic rays, a global magnetic field that deflects solar storms, a surface gravity of 1 g to which human physiology is fine-tuned, vast oceans of liquid water, abundant atmospheric nitrogen, and an existing resilient microbial biosphere that will recover over time. On a post-apocalyptic Earth, a survivor can step outside a shelter without wearing a pressurized spacesuit. They can breathe the air without dying of hypercapnia or oxygen deprivation within 3 minutes. They do not face continuous galactic cosmic ray bombardment that causes secondary neutron spallation inside their living quarters. Their bones will not dissolve at a rate of 1% per month, and their children will be born under the natural 1G gravity in which mammalian reproduction evolved. To flee a damaged Earth to settle on Mars is like jumping out of a damaged house with a leaking roof into the middle of a burning blast furnace. This perspective shift does not mean that humanity should abandon space exploration or give up on sending humans to Mars. Exploring Mars is one of the most exciting, scientifically valuable, and inspiring endeavors our species can undertake. Robotic rovers, orbital mappers, and eventual short-term crewed scientific outposts similar to our research stations in Antarctica will yield extraordinary discoveries about planetary evolution, the history of water, prebiotic chemistry, and the potential existence of ancient microbial life in the red subsoil. We can and should send scientists, geologists, and engineers to Mars to explore, learn, and push the boundaries of human knowledge. However, we must strictly separate scientific exploration from the illusion of permanent, self-sustaining civilian colonization. An Antarctic research station is a brilliant success of human science. It is not a self-sustaining city. The scientists at McMurdo Station do not attempt to raise families, build semiconductor foundries, or establish an independent nation in the ice. They conduct vital research while remaining entirely dependent on continuous resupply from temperate nations. Human outposts on Mars will function under the exact same paradigm. They will be high-tech, highly specialized, temporary scientific outposts sustained by an umbilical cord connected directly to Earth. The dangerous tragedy of the Planet B ideology is that it breeds a subtle, unconscious form of environmental defeatism on Earth. When people believe that Mars offers an alternative home for humanity, a clean slate, where we can start over after spoiling our current world, it reduces the perceived urgency of preserving Earth's biosphere. It encourages a hubristic belief that technology can easily replace the complex, 4-billion-year-old ecological infrastructure that keeps us alive. But technology cannot replace a biosphere. If we cannot manage the climate, preserve the oceans, protect the soil, and maintain ecological balance on a lush, ocean-covered planet where life evolved naturally, we have zero chance of engineering an artificial biosphere on a frozen, toxic, airless rock 400 million kilometers away. Preserving planet Earth is not one option among many. It is the absolute non-negotiable prerequisite for the long-term survival of consciousness in the universe. Earth is not a disposable cradle to be discarded once we learn to build our rockets. It is our single, solitary home in a vast, silent, overwhelmingly sterile cosmos. Every breath of air we take, every glass of liquid water we drink, every seed that sprouts in soil, and every heartbeat that pumps blood smoothly through a body designed for 1G gravity is a gift granted by a planet that is unique beyond imagination. As we gaze out at the salmon-coloured skies of Mars through the cameras of our robotic scouts, we should marvel at the cold, quiet beauty of the red planet. We should send our bravest explorers to plant boots in the dust, collect core samples, and unravel the ancient history of a world that once had rivers and seas. But as those explorers look up into the dark Martian sky, searching for a tiny blue point of light gleaming among the stars, they will understand the true lesson of interplanetary spaceflight. They will see Earth not as a problem to be escaped, but as a priceless cosmic miracle, a glowing blue sanctuary floating in an infinite hostile void. They will realize that the true purpose of traveling to Mars is not to abandon our world, but to look back across the dark gulf of space and finally realize just how precious, how fragile, and how irreplaceable Earth truly is. Survival does not lie in building cities in the red dust of a dead planet. Survival means protecting the single living world we were blessed to inhabit, ensuring that the light of human consciousness continues to shine brightly on the only home we will ever have. To summarize this ultimate cosmological synthesis, consider the profound balance between human ambition and biological reality. Our drive to explore deep space is a testament to the curiosity, intelligence, and courage that define humanity at its best. By building rockets, landing rovers, and designing life support systems, we push our technological capabilities to their absolute limits, inspiring generations to study science, mathematics, and engineering. Yet true wisdom requires recognizing the limits imposed by natural law. We must honor the laws of physics, the constraints of thermodynamics, and the biological parameters of our evolutionary heritage. Exploring the solar system while preserving Earth's biosphere is not a contradiction. It is a unified strategy for long-term survival. We step out into the stars not because we can leave Earth behind, but because exploring the void deepens our reverence for the fragile blue marble that birthed us, ensuring that our species remains anchored in reality while reaching for the stars. Ultimately, evaluating the Mars colonization debate brings us back to the primary truth of space exploration. Mars will challenge us, educate us, and humble us. It will show us the absolute power of technology to expand our vision, alongside the absolute limits of technology to sustain life outside its natural ecological home. As long as human civilization endures, the Red Planet will remain a beacon for science, discovery, and international cooperation, a testament to human ingenuity working in harmony with the undeniable truth that Earth is, and will always be, our only true home in the universe. Finally, contemplating the human future in the cosmos reinforces the ultimate purpose of planetary science. Exploring Mars and understanding its physical limits teaches us the true value of Earth's biosphere. The Red Planet serves as a cosmic mirror, reflecting the absolute uniqueness of our terrestrial home and challenging us to act as responsible stewards of the only living world we know. By focusing our creative energy, scientific talent, and financial resources on preserving Earth's environment while conducting careful, curiosity-driven exploration of space, we achieve a balanced, sustainable path forward. Humanity will continue to send robotic scouts and brave human explorers to Mars, but we will do so with clear eyes and humble hearts, knowing that while our curiosity reaches across the stars, our home will forever remain rooted on planet Earth.